So we now look at a new problem which has a greedy solution, a problem of job scheduling with deadlines. Now job scheduling comes in many flavors. We already looked at one task scheduling problem as an example when we discussed and we introduced greedy algorithms. So there we had to schedule tasks across a number of machines. So here we have a different situation. So we have jobs to be done on a single machine. We don't have the possibility of moving to different machines. Okay? So each job takes unit time. So it takes only 1 unit of time to execute. Okay, it has a deadline di and it has a profit or a value pi. Okay. So we have a bunch of jobs. Each job takes unit time. So the amount of time it takes to finish is just 1 unit of time. But each job has to be finished by a certain deadline and it has a certain profit. And of course, you get this profit, okay, is paid. The profit is paid only if I is completed before di, so within its deadline. And of course, the constraint on the machine is the machine can only do one job at a time. So at each unit of time, the machine has to choose a job to execute and can only do one job. Right? So now the problem that we are trying to solve is to select a feasible subset of jobs to maximize the profit. So here by a feasible subset, we need a set of jobs which can be completed within their given schedules with their given deadlines, because there's of course no point in choosing a job to do if you can't meet the deadline, you get no profit. So if you want to maximize profit, it is sufficient to look at those jobs which can be done within their given deadline, but not all jobs may be feasible, so you have to select some suitable subset, so it becomes an optimization problem. So let's look at a small example. Here we have 4 jobs. Their profits are 100, 10, 15 and 27 and their deadlines are 2, 1, 2 and 1. Now this is actually a small enough sample that we can actually exhaustively enumerate all the feasible solutions. Okay, so let us look at what all the possible feasible solutions for this problem are. So here is the set of all feasible solutions. Now it turns out that we can only do at most 2 of the 4 jobs because of the constraints. They must all finish within 2 time units. So we only have 2 slots in which to do them. Some combinations are not compatible. In particular 2 and 4 for example are not compatible because they must both be completed within the first time unit. So there's no way we can do them both at the same time. On the other hand, we can do for example 1 and 2 but reverse them. So we do 2 followed by 1, or we can do 2 and 3 by doing 2 before 3 and so on, and each of them has some given profit associated with it, given that. So if we do 1 and 2 I get 110 and so on. And in this particular thing, notice that some things admit multiple schedules. If I do 1 and 3, both need to finish only by the second time unit, so it doesn't really matter whether I do 1 followed by 3 or 3 followed by 1. Now in this particular thing, it turns out that the best option is to do 1 and 4. And here actually the greedy strategy is fairly clear because there is only one quantity more or less that one has to worry about, which is the profit. And so it turns out that the greedy strategy is to order by decreasing profit. So in this example, if we order this by decreasing profit, then the most profitable job is 1, so we try that first. Then the next most profitable job is 4, so we try that next. And the next is 3, and the next is 2. So this is the sequence in which we try out jobs. And as before, what we have to do is for each job that we try out, we have to verify that adding that job preserves feasibility. None of the jobs we have taken earlier become infeasible or start missing their deadlines because of adding this. So here is a high-level description of the algorithm that we have in mind. So we have an algorithm greedy job which takes as input D, which is a sequence of deadlines, okay? And it has N, which is the number of jobs, and we have a parameter j, which is a feasible subset we're going to pick and return. Okay? So now what is assumed in this is that we have given that P1 is bigger than or equal to P2 and so on, bigger than or equal to Pn, but we don't actually need to know these profits. Right? We are just going to assume that as we go along, each job we pick has a lower profit than the previous one. We just have to ensure that the jobs can be included based on the deadline. So the only useful information we need are deadlines. The other thing we need to know is that each deadline is at least one. Okay? So this means that if supposing a deadline is 0 or less, that means this job can never be scheduled. So we might as well discard it from our problem statement together, because any job which cannot be scheduled is never going to be part of any solution. So we assume that all jobs can be scheduled at least in the first instance. So this means that the very first job is always feasible because it's the highest price job. It has a deadline at least one. So we initialize our solution to include the first job. So given this, then we proceed to the other jobs. So for each new job from 2 to n, we see if we can add the new job to the current set j while maintaining feasibility. In other words, j already has a set of jobs which can be scheduled. We don't want to disturb that. We don't want to discard a job we've already selected. So we want to check whether I can be added to j without disturbing feasibility of j, and also I remains feasible in the new set. If so, we update j to include I. If not, we skip I and we go ahead. Okay? So in this way, we keep going one pass from 2 to n, and at the end, whatever jobs we collected in j, that is the optimum set that our greedy algorithm has constructed, and we return it. So one crucial thing that needs to be computed is this property. Right? How, when we pick up a job I, do we determine whether adding I to j retains feasibility or not? Right? So in general, the question is, given a set of jobs j, when is j feasible? Okay? When can I schedule all the jobs in j according to their deadlines? Okay? Now, there would be, of course, a brute force approach to this which will work, which is to try all permutations, right? So every feasible schedule is some permutation. So we try all permutations and check for each permutation whether each job is within its deadline, but clearly this is a highly inefficient thing. So what we will actually do instead is make the following observation, okay, that j can be scheduled in increasing order of deadlines. Okay. So this simplifies. We don't have to look at all permutations. We only have to look at one permutation. We will justify this later on. But what we are going to observe is that j can be scheduled in increasing order of deadlines. So formally, we have a result which is called theorem 4.4 in the textbook. And this says that if j is a set of jobs numbered 1 to k with the assumption that the deadlines are in order. So the deadline of 1 is earlier than the deadline of 2, which is earlier than the deadline of 3, and so on, which is earlier than the deadline of the kth job. So they are ordered in the sequence of their deadlines. Okay. Then suppose j is feasible, that is, there is a way of executing all the jobs in j within the deadlines. Then this is the case if and only if the sequence 1 to k is a feasible order. Right? So of course, if 1 to k is a feasible order, j is feasible. So really the crux is to show that any feasible solution for j implies that 1 to k is a feasible solution. Right? So now we are not going to prove this now. We will prove this later when we also prove that the greedy strategy is optimal. But how do we use this? Okay. So to use this fact, okay. So then what it means is that to check that j is feasible, all we have to do is first sort it by deadlines, and then we have to check that each job meets its deadline. But we know exactly when each job takes place, right? Job I happens at time I, so we have to check that the deadline of job I after the reordering, so I is the new position, is bigger than or equal to I itself, because this is the time. okay, for every I. So checking that each job meets its deadline in this particular sequence is very easy. We just have to check that di is bigger than or equal to the instant I at which that job is going to be scheduled. Right? So if we assume this theorem, then checking that j is feasible just amounts to keeping this sorted set and checking that every position is greater than, every deadline is greater than the position at which it occurs. So let's use this theorem to solve our problem of extending j to j union I. Okay? So we have an existing set j, so this is the current solution. And what we assume is that this current solution is actually arranged. So we have j1, j2 up to jk as our current solution, and this is arranged in the order of deadline. So you have d1, which is less than or equal to d2, which is less than or equal to d3, and so on, and which is less than or equal to dk. And now we want to extend this solution to include I. So we have a new element I which comes in, and it has its own deadline di, and we want to figure out whether it's feasible or not. So what we do is we first start from one end, say from the right, and we find a position to insert I so that di fits correctly in this ordering of the deadline. So it's like inserting an element into a sorted list. Having done this, we have to check two things. One is we have to check that I itself is feasible. That is, that at the position where I insert, di must be bigger than or equal to the insert position. So the deadline is met at this position. The other thing we have to check is that everything to its right is now going to be shifted by 1. All these deadlines were feasible when they were in their current positions. Do the deadlines remain feasible after shifting by 1? If both of these conditions hold, then this is okay. If any of these conditions fail, then we have to discard I and go to the next job. So here is our detailed solution to the job scheduling problem using our greedy strategy. So as before, we have the sequence of deadlines assumed to be in decreasing order of price, and we have the number of jobs, and the set we are going to construct and return is the set J. So now remember that we are going to maintain our jobs as a sequence, the jobs in the feasible set so far, as a sequence sorted by increasing order of deadline. And we are going to try and insert each new job into the sequence in order to determine whether or not it can be added without disturbing feasibility. So for this, we have these dummy values at the beginning of the sequence, which will be helpful for inserting, okay, as we will see. Now, as before, we should note that initially we start with the set J1 containing first job 1 because this job is always feasible. So K is the size of J. So at any given point, we have so far included K jobs in our feasible set. So for each job that we add, we have to check whether that job can be inserted into the current sequence J, which is an increasing order of deadlines. Okay? So we have J, which is of the form J1, J2, so actually J0 to Jk. So J0 is this dummy job, right? And then we start by setting a pointer R equal to K. And what we do is we walk left. So we keep doing R equal to R minus 1, subject to two conditions. The first condition is that we are trying to insert the new job. So we are checking whether the deadline of the new job, which is D of I, is smaller than the deadline of the job we are looking at. Because we are, remember that these deadlines are in decreasing order. So D0 is less than equal to D1 is less than equal to D2 is less than equal to DK. So we are trying to find the correct position to insert. So that is what this is doing. Now the other thing that we are doing is simultaneously checking whether the effect of inserting will affect feasibility. So remember that initially this job was feasible, right? So for every position we had that the position I, okay, was less than or equal to di. Now when we shift right, is going to increase by 1. So what we are checking is that is I actually strictly less than di. If I is strictly less than di, then I plus 1 will be less than equal to di. So shifting by 1 will not affect the feasibility of the job at position I. So that is what this is doing, right? So this is really checking whether the deadline is strictly greater than R. If it is strictly greater than R, then I can afford to increase the position and nothing will happen. Okay? So I go through this and I exit this loop for one of two conditions. Either I found the correct position to insert, or I found a job which cannot be moved to the right without affecting feasibility. So that's what I check here. So if I come here and I find that in fact I have found a position, okay, where I have stopped with a deadline which is smaller than the deadline I'm looking at now, right? And this particular deadline is feasible. Right? So this says that job I is feasible at the insertion point. Okay? So if I found the correct position and that position is feasible, then what I do is I take everything to the right, okay, from R plus 1 up to K, I move everything to the right. I move Q to Q plus 1. And finally, at position R plus 1, I insert I and I increase the size of the set to K plus 1. Right? If either of these conditions fails, either I was not able to find a position, or at the position I have found, the job I want to insert is not feasible, then I would skip this step and J will be unaffected. So I go through this for each job from 2 to n, and eventually I return the set J that I have constructed. So we have seen one version of job scheduling, okay, with unit time, deadlines, single machine, okay, and profit only if deadline is met. And this has a greedy solution. Now there are many variations. We have already seen one variation earlier. So we could have one machine or many machines. Okay. We can have durations. So you can have start times and end times. So this was a variation that we saw right at the beginning, where we had many machines, but each job had an interval within which it must take place. The other thing is that we could have this kind of 0-1 profit, that is either you get the profit or you don't, or you could have a penalty for delays. Right? In some situations, you lose some money, but not all of it if a job doesn't finish. So by degrading your solution, by moving some things a little further, you might lose some money on some jobs, but that might be compensated by getting more money on other jobs. Okay? So depending on which combination you choose, you may or may not get a greedy algorithm. Some of them are greedy, some of them use a technique that we will see later called dynamic programming. Okay? So depending on the exact flavor of the problem, the algorithm that you have to choose will vary. And so one has to look at the parameters carefully. And always when one has a greedy solution, you must always prove optimality. So far we have not proved optimality. We have actually done two things that we have not proved. One is we have used a lemma about job scheduling, saying that a set of jobs is schedulable if and only if it can be scheduled in the order of their deadlines. And secondly, we haven't shown that the schedule that our greedy algorithm actually produces is optimal. So we will prove these both later, but it's important to see that job scheduling is a very canonical problem in computer science and in real life as well. And depending on the parameters that go into the problem, different types of algorithms may be required.